Welcome students. For the convenience, I can divide the rotational dynamic chapters in two parts. In first parts, we learn about the circular motion. In the first parts, we learn about the characteristics of circular motion, kinematics and dynamics of circular motions, applications of horizontal circular motion and vertical circular motion. Now today, I am going to second parts of rotational dynamics. The second parts contains the topics moment of inertia. Moment of inertia is analogous for mass, kinetic energy of rotating body, moment of inertia of thin uniform ring, moment of inertia of thin uniform disk, radius of gyration, theorem of parallel axis and theorem of perpendicular axis, angular momentum, or that is also called moment of linear momentum, expression for torque in terms of moment of inertia, conservation of angular momentum, and last topic is rolling motion. After learning these topics, the student must visualize the concept of moment of inertia of an object. Student relates the moment of inertia of body with its angular momentum. And student differentiate between the translational and rotational motions of rolling objects. These are the objectives of the topics after learns. Now, today I am going to explain the moment of inertia of the body. Before that, we must recall some concepts which we have studied in 11th standard. In 11th standard, we study the rotational analogy of force is a moment of force or torque. This point is already studied in 11th standard. Rotational analogy of a force is a moment of a force or torque. Before explain these topics, I show one video, and from that video we compare what is meant by translational motion and rotational motion. What is meant by translational motions and rotational motion? Here, a man gives the force to this wheel of the bicycle, and due to that force, the wheel rotates about its axis shown here. This is the rotational motion. This is the rotational motion, not translational motion. This is the rotational motion and not translational motion. In this motion, the particles can be revolved around the center of mass point. Revolves around the center of mass point. And every particles have different linear displacement. The particles which is at the rim of the wheel that travels larger distance as compared to the particles nearest the axis. Nearest the axis. That means every particles have different linear displacement. Different linear displacement, but same angular displacement. But same angular displacement, such a type of motion is called the rotational motion. Such a type of motion is called rotational motions. In here, the man carrying the bicycles on his shoulder. In that case, the force is acts on the different particles. The net force is acts on the center of mass point. And due to that, all the particles of the bicycles travel the same distance along the same line, or parallel to the center of mass points. Such a type of motion is called the translational motion. Such a type of motion is called the translational motions. Both the motions are also observed from this. Here in my palm of left hand, a mobile is placed in rest positions. Here I applied the force along the center of mass point. Observe the motion of the mobile on my palm of left hand. Here, as the force applied at that time, the mobile moves along the direction of force applied. And we see that all the particles travel the same distance parallel to the center of mass point. Such a type of motion is called translational motion, just like as the bicycle carried by that man. Bicycle carried that man. But when we applied the force except the center of mass point, here I applied the force. Observe the motion. Observe the motion. Here, the mobile performs rotational motion, not translational motion. In this motion, we observed that the particles near this center of mass travels small linear displacement, but the particles which is at larger distance, that is at the end of the mobile, that travels larger displacements, but same angular displacement. Such a type of motion is called the rotational motion. In translational motions, center of mass is in motion along the straight line path. Also, every particles are along the straight line paths parallel to the center of mass point. But in rotational motion, all the particles are moving around the center of mass point. Such a type of motion is called the rotational motion. Translational motion is due to the net force act on the center of mass point of the body, and rotational motion caused by the net torque acting on the body. Torque is produced due to the force acting on the body except its center of mass point. Hence, torque is also called as moment of force. That is the ability of rotation. That is called the torque. According to Newton's second law, force is equal to mass into acceleration. This is for translational motion. In rotational motion, the expression for torque can be found out in 11th standard, and that is with the help of the example which is observed in our daily life, that is to open or close the door. That is to open or close the door. This picture shows the top view of the door. This red color points show the axis of rotation of the door. This is the other end of the door. When we applied the force perpendicular to the surface of the door at the other end, at that time the door gives the turning effect. We observe the turning effect of the door. If this force is smaller, angular displacement is smaller. As we applied the larger force, at that time angular displacement is larger. We observed in our daily life. That means moment of force depends upon the magnitude of the force. Magnitude of force. Also, if we applied the force toward the point near to the axis of rotation, here F2 force is applied, and at one end F1 force is applied. If due to this F1 force, if the angular displacement is possible theta, at that time the magnitude of force required at the point near to this axis of rotation is larger. This second force is larger for the same turning effect. For the same turning effect, this force must be larger. That means from this we conclude that the turning effect or the moment of force is also depends upon the position at which we applied the force. If we applied the force at larger distance from the axis of rotation, we required small magnitude of the force. But when we applied the force near to this axis of rotation, we required larger amount of force. Also, if we applied the force parallel to the surface of the door or along the direction of the axis of rotation toward this axis of rotations along the position vector, at that time door cannot perform any motions and any rotational motions. Rotational motion त्यावेळेस perform करणारच नाही. Also, if the force is applied inclinely to the surface of the door like this, at that time also the turning effect depends upon this angle. If this angle is larger, moment of couple is larger. If this angle is smaller, turning effect is smaller. Since this perpendicular distance is different for different angle. This perpendicular distance is larger when the angle is larger. This perpendicular distance depends upon the sine of theta. As theta is larger, perpendicular distance is larger. This can be explained by using this formula. In standard 11, we take expressions for torque is equal to, in vector form, torque is equal to vector r cross vector F, where vector R is the position vector at which we applied the force from the axis of rotation. This is the position vector, and vector F is the applied force along the directions. This is the expression for the torque. The magnitude of the torque is tau is equal to R into F into sine theta, where theta is the smaller angle between vector R and vector F. Vector R and vector F. From these diagrams, from the right angle triangle, OPQ, vector OQ is, or vector, sorry, OQ is the R sine theta is the perpendicular distance to the line of action of this force, from the axis of rotation. This perpendicular distance is called the moment R, that can be represented by R perpendicular. Hence, instead of R sine theta, we write R perpendicular. Also, if this force can be resolved into two components, one is F sine theta perpendicular to the surface of the door, and another is F cos theta, which is along the position vector. Due to this force F cos theta, there will be no turning effect, but due to this perpendicular force, the door gives the turning effects when we applied the force, perpendicular force. This perpendicular force is F sine theta. The magnitude of this perpendicular force is F sine theta. Therefore, instead of F sine theta, we write here F perpendicular. This is the magnitude of torque or moment of force. The turning effect depends upon, as the position and the magnitude of the force remains constant. At that time, the turning effect depends upon this angle between position vector and direction of force. If this angle is larger, that is equal to 90 degree, at that time the torque is larger. Or turning effect is larger. Turning effect is observed larger. This is the expression. That means from these 2 points, translational motion and in rotational motions, the force here, this force produces translational motion and torque produces rotational motion. Thus, it is clear that torque or moment of force to produce a rotational motion is analogous with a force which produces translational motions. This point we have already studied in the 11th standard. Also in 11th standard, we study that the torque is a vector quantity and its direction can be found out by using the right hand thumb rule. Here, a rigid body, and when we applied the force to this body in such a way that the body performs anti-clockwise signs when we observe from the top sides like this. If this is the axis of rotation, these fingers are the axis of rotation, and when we applied the force to this directions, along these directions, at that time the mobile get rotated about this axis of rotation, The direction of force is along these directions, and the position vector is along this direction. Position vector is along this direction. If we place our right hand along the direction of the position vector and fingers are cursed towards the direction of line of action of the force, line of action of the force is along the directions, then from vector R to vector F, and thumb is outstretched along the axis, then that outstretched thumb denotes the direction of the torque. This torque is vertically upward directions, vertically upward directions, upward directions. When this is horizontal circular motion. But if this is vertical circular motion, vertical circular motions, at that time the thumb is towards you, towards you. Hence, that is considered as a positive vector. That is considered as positive vector. That means in that case, torque is positive. That can be shown in first figure. See, if the force is applied along these directions, see here, if the force is applied along these directions, observe this. At that time, the mobile rotates along the clockwise sense, along the clockwise sense when we observe from top view, top side. In that case, place the palm of our right hand along the direction of position vector and fingers are curved toward the line of action of the force. Position vector is along the directions and line of action is along the directions. Therefore, from position vector toward the line of action of the force and thumb is outstretched, at that time the thumb denotes the direction of torque, that is downward direction, that is considered as a negative in case of horizontal circular motion. In case of vertical circular motions, this is clockwise directions, and in that case the thumb is away from you. That means that is considered as a negative vectors. That is considered as a negative vector that can be shown in the second figures. That can be shown in the second figure. These points can be studied in 11th standard. Now, today I am going to explain the moment of inertia, which is the topics in our 12th standard. Instead of this rigid body, if this rigid body has the mass m, capital M, if that mass is situated, small m, if that mass is situated at this point P, single point consider. Instead of rigid body, we consider single particles. And if we applied the force in such a way that it performs circular motion along this anti-clockwise sense, at that time, according to Newton's second law, for translational motion, the expression for the force F is equal to mass into acceleration. In magnitude, it is equal to mass into A, m into A. Vector notation, that's current. Due to that force, this object performs circular motion. If you consider only single particles, if that is rigid body, at that time that body can be rotates. Hence, here we consider as rotational motion. In rotational motion, instead of circular motion, we write here rotational motion. The expression for the torque produced angular effect is torque tau is equal to vector R. This is the position vector from the center, and this is the applied force. This is the line of action of the force. In magnitude, torque tau is equal to R into F into sine theta. Here, the position vector is along the direction and vector F is perpendicular to the position vector. That means angle between vector R and vector F is 90 degree. Therefore, this is equal to R into F. Since sine 90 is equal to 1. Therefore, torque tau is equal to R into F. But according to expression for the force is equal to mass into acceleration. That is m into a. That's when torque tau is equal to r into m into a. But in circular motions, acceleration a is equal to r into alpha. Therefore, the expression for the torque tau is equal to, therefore, expression for torque tau is equal to r into m into r into alpha. R into m into r into alpha. And that is equal to mr square into alpha. Let this mr square is represented by I. Instead of mr square, we write here I. That is called moment of inertia. That is called moment of inertia. So the expression for the torque tau is equal to I into alpha. This is the expression for torque tau for a single particle. For a single particle, tau is equal to I into alpha. Here, this is the expression second. From equation first and second, it is clear that torque is analogous with the force and angular acceleration is analogous with the linear acceleration. We have already studied. That is, we studied that the alpha is analogous with the acceleration. Alpha is angular acceleration and a is linear acceleration. Both are analogous to each other. Also, in alien standard, we studied that the torque is analogous with the force F. So the remaining third quantity in this figure is, in this formula, is mass, and here the remaining quantity is I. That means I is also analogous with the mass. From equations first and second, it is clear that torque is analogous with the force and angular acceleration alpha is analogous with the linear acceleration A. Thus, the moment of inertia I is analogous with the mass. This is the analogy of moment of inertia and mass. In linear translational motion, mass represents the inertia in translational motion, since the mass opposes the translational motion. That can be explained with one of the example. If a car and a heavy vehicle like truck or road roller are rest on the same road, are steady on the surface of the road, that's a steady, that's a rest. If we give some force to change its state, that means both are in motions. For that purpose, we must require some force applied to the vehicles. We observed that large amount of force will be required for the motion of a truck or roller as compared to the car. This is due to the truck or road roller have larger mass as compared to the car. That means mass represents the inertia. Mass represents the opposition to the motion. That means in translational motion, mass represents the inertia. Similarly, I, that is the moment of inertia in rotational motion, represents the inertia in rotational motion. That is also called rotational inertia. This is the physical significance. Of moment of inertia. This is the physical significance of moment of inertia. Remember these things. Here we define the concept moment of inertia. Moment of inertia can be defined here, and its definition is with respect to a specific axis of rotation. Specific axis of rotation or given axis of rotation. In first figure, O is the O point is the axis of rotation and P is the point where the object is situated. Here we consider the single point mass. Here we consider a single point mass. In these first figures, we consider a single point mass and O is the axis of rotation. If these single particles can be revolves around this point O, around this point, at that time the moment of inertia of the single point, the moment of inertia of a point mass with respect to an axis, is defined as the product of mass times the square of distance from its axis of rotation. Now here, the single particle has a mass. If we consider this single particle has a mass capital M and R is the distance of these particles from this axis of rotation, then the moment of inertia of the single particle is equal to m into r square. This is the expression for the moment of inertia of a single particles. But in our daily life, such a single particle cannot be in existence. Now, if we assume the body is made by number of such particles which have different masses, like this in second figures. In second figures, this body is consist by the particles, number of particles having masses m1, m2, dash, mn, and which are situated at a distance r1, r2, dash, rn from this axis of rotation. That means we consider the body is the collection of point masses. At that time, the moment of inertia of such a collection of point masses is equal to the sum of the moment of inertia of individual particles from the given axis of rotation. That is, I is equal to m1 into r1 square plus m2 into r2 square plus m3 into r3 square plus dash plus mn into rn square. That is equal to summation of mi into ri square, where I is equal to 1 to n. If we assume the body is the collection of point mass, but in our daily life, the body is a rigid body whose mass is continuously distributed, that masses cannot be separated from each others. At that time, we can find out the moment of inertia by replacing summation as integration and mass of single particles. Instead of, we assume a small element having the mass dm. Instead of particles, we consider small element of that particles that have mass dm and which is situated at a distance small r. At that time, the moment of inertia of such a rigid body which is shown in figure 3rd, is equal to integration of r square into dm. Here the mass can be changes from 0 to capital M. These are the expressions for the moment of inertia of single particles, for collection of point masses, and for a rigid body. The SI unit of moment of inertia is the product of mass and square of distance. Therefore, its SI unit is kilogram meter square and CGS unit is gram centimeter square. The dimension of moment of inertia is L square m and t raised to 0. L raised to 2, m raised to 1, t raised to 0. This is the dimension of moment of inertia. Now, on which factors the moment of inertia depends? On which factors the moment of inertia depends? If we assume that we consider a solid cylinder or the body which have the same mass, If I show here two objects. One is this is eliminator or charger. This is bad. This is mobile. If both have the same mass, दोघांचं mass सारखं आहे. दोघांचं mass सारखं आहे. That is depends upon moment of inertia depends upon the mass. If mass is different, moment of inertia is different. Mass is different, moment of inertia is different. Also depends upon the shape. If the mass are same, but the sizes are like this, if both have the same mass, and axis of rotation is this their center of masses, at that time this mass is closer to the axis of rotation. This mass is wide, this mass is widely distributed from the axis of rotation. Therefore, the moment of inertia of both the bodies are different. That means moment of inertia of the body depends upon the mass, shape, and size of the body, distribution of mass in a body about an axis of rotation, position and orientation of axis of rotation. For example, if we consider a solid cylinder about its own axis, the moment of inertia is mr square by 2. But when that can be pressed by using hammering, its mass can be widely distributed. Its shape can be changed. Instead of solid cylinder, we converts it into disc-like, and the distribution of the mass is widely separated as compared to the solid cylinder. So their moment of inertia are different. Shape change केला तरी त्याचं हे चेंज होईल, moment of inertia चेंज होईल, साइज चेंज केली तरी चेंज होईल. Axis of rotations आपण चेंज केला, positions, if this is the axis of rotations, the moment of inertia is different. But if we consider this is the axis, at that time distribution of mass is larger as compared to this axis. Therefore, the moment of inertia is different for the same body if the position of the axis can be changes or its orientation can be changed. If we consider the axis of rotation is along these directions, that means the moment of inertia is different for the different position of axis of rotations and orientation of axis of rotations. These are on these factors the moment of inertia will be depends. Thank you. Now, if we like this video, subscribe with my channels. If we like this video, subscribe to my channels RD Patil, and after subscribe, press the bell icon buttons for next videos notifications. Give the comments on the comment box. Thank you.